The process by which an ionic compound dissolves is also an equilibrium process. This is not referring to compounds that are soluble, like sodium chloride. It's not an equilibrium process. It completely dissolves. It's all sodium ions and chloride ions. It refers to what we have previously called insoluble compounds. It turns out these insoluble compounds are just very, 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 very slightly soluble. Only a very small amount of ions would be present in that solution, and that is an equilibrium process. So the equilibrium expression for a chemical equation that represents dissolving of an ionic compound is called the solubility product constant, or Ksp. Ksp is really no different from KEQ. It's just a special name because it, is dealing with this dissolving of a solid. Just like when we were writing KEQ expressions, you do products over reactants. Just like when we were writing KEQ expressions, any coefficient is going to become an exponent. And just like when we were writing KEQ expressions, solids are omitted from the equilibrium expression. Change that. All right. So to write an expression for Ksp, you first have to show the solid dissolving, and then just write the expression the way that you wrote the KEQ expressions. So barium sulfate solid is dissolving. It is in equilibrium with one barium ion and one sulfate ion. Those ions are dissolved in water, and so the state when something is dissolved is aqueous. So when I'm writing my Ksp expression, it would be the concentration of the products over the concentration of the reactants. But notice my reactant, my reactant is solid. And just like with KEQ, you do not include solids in your equilibrium expression. So your KSQ or Ksp expression is just that, barium times sulfate. With this manganese hydroxide, that's going to dissolve into one manganese ion and two hydroxide ions, because there's two of them in the formula. So my Ksp expression is going to be the concentration of manganese times the concentration of hydroxide squared. And then lastly, silver chromate is going to dissolve into two silver ions plus a chromate ion. So my Ksp is going to be silver ions squared times chromate. So really not any different from what we've been doing. It's just an SP instead of an EQ. And Ksp, just like with KEQ, the magnitude of Ksp can tell us a lot about what's going on. If we have a large Ksp, that means that the forward reaction is favored and we're going to have a more soluble compound. You're going to have more ions present at equilibrium. A small Ksp means that it is a less soluble compound. It means the reactants are favored. So you're going to have very few ions present at equilibrium. Large and small doesn't have a definitive cutoff. You really would just have to compare to like it's doing in this question here. So what is more soluble, calcium sulfate or silver chloride? So here's calcium sulfate, 7.1 times 10 to the negative 5. Here is silver chloride, 1.77 times 10 to the negative 10. So the more soluble compound is the calcium sulfate because it has the larger Ksp expression or value, Ksp value. It's negative 5, whereas the other one is negative 10. Notice we have copper sulfide, 10 to the negative 36, extremely insoluble. You're going to have basically no ions present at equilibrium with that one because it has such a small value of Ksp. You can use Ksp to determine what's called the molar solubility. The molar solubility is the solubility of an ionic compound in moles per liter, or molarity, and you can calculate that from Ksp. So if I have the KSP value of solid silver chloride is 1.77 times 10 to the negative 10, and I want to calculate the molar solubility of silver chloride, we are going to start with writing our solid silver chloride dissolving. So that's going to dissolve into aqueous silver ions and aqueous chloride ions. We can write our equilibrium expression. So Ksp is the concentration of silver times the concentration of chloride. And I have a value for Ksp. Ksp is 1.77 times 10 to the negative 10. But I have to then calculate the molar solubility, and that seems challenging because it seems like I have two variables. I have concentration of silver and I have a concentration of chlorine. But I don't actually have two variables because whenever 1 mole of silver chloride dissolves, it's going to dissolve into 1 mole of silver ions and 1 mole of chloride ions. So I don't know the molar solubility of silver chloride, so we'll call it X. But that means silver would also be X and chloride would be X because of the ratio, because it's all a coefficient of 1. So really what I end up with is 1.77 times 10 to the negative 10 equals X times X, or X squared. So of course, to get X by itself, you would square root both sides, and you would get 1.33 times 10 to the negative 5 moles per liter. So that is my molar solubility. 1.33 times 10 to the negative 5 moles of silver chloride will dissolve per liter of water, or of solution. If I was then asked to calculate my concentrations of silver and chloride at equilibrium, I could do that, where silver is 1.33 times 10 to the negative 5 and chloride is 1.33 times 10 to the negative 5. Actually, I'm going to say moles per liter. Moles per liter. So that's not actually calculating the molar solubility, but you might be asked to calculate the ion concentration as well. The Ksp value of lead to chloride is 1.17 times 10 to the negative 5. So this one is similar with an extra little added twist. So lead to chloride, solid, dissolves into aqueous lead 2 ions and 2 chloride ions. So my equilibrium expression is going to be concentration of lead ions times concentration of chloride ions squared. Now, again, if my molar solubility of PbCl2 is X moles per liter, then lead will also be X moles per liter because it's a coefficient of 1, but chlorine is going to be 2X moles per liter because it has that coefficient of 2. So when I go to plug this in, 1.17 times 10 to the negative 5 equals, I'm just going to plug in X for lead. I'm going to plug in 2X for chlorine. So I'm going to get X times 2X squared. Of course, that squared will distribute. So I'll end up with 1.17 times 10 to the negative 5 equals 4X cubed. So to solve, right, first we're going to divide by both sides by 4, which is going to give me 2.925 times 10 to the negative 6 is X cubed. And then, of course, to get X by itself, to get rid of that cube, you take the cube root, and you're going to get 1.43 times 10 to the negative 2 moles per liter. So again, if I was solving for my lead ions, that's going to be 1.43 times 10 to the negative 2. My chloride ions is 2X, so it's going to be 2.86 times 10 to the negative 2. But I guess, well, this is actually the answer, the molar solubility. Finally, given molar solubility, you can calculate Ksp. So the molar solubility of copper bromide is 2.0 times 10 to the fourth moles per liter. So that's my value of X. I'm given X, and I'm solving then for Ksp. So copper 1 bromide, solid, dissolves into aqueous copper 1 ions and aqueous bromide ions. So my Ksp is going to be concentration of copper times the concentration of bromine. And again, that's what I was given in my, by being given the molar solubility. So Ksp is going to be, they're both X, right? Because they're both a coefficient of 1. So copper is 2.0 times 10 to the negative 4. Bromine is 2.0 times 10 to the negative 4. So my Ksp is going to be 4.0 times 10 to the negative 8.